Alright, so we're going to be solving the neutron diffusion equation for slab geometry. Alright, so we got the time-dependent neutron diffusion equation here, but we're going to make some assumptions to make it simpler. We're going to make it from a partial differential equation to an ordinary differential equation. So our first assumption is that it's going to be steady state, which means no time dependency. We're considering our reactor or our multiplying material to be critical, so our neutrons aren't going to change with time. So we say our d phi over dt is going to equal 0. Sixth assumption is that we're going to say that fixed first law of diffusion is valid. So because we have here our d, which is our diffusion coefficient, kind of based off material science diffusion. So we say that's valid, so we can have our diffusion coefficient. And then we're going to have a homogeneous material. This is just saying that our cross sections isn't going to change with space. So you can see that with our sigma A and our sigma F, it depends on R. So saying that it depends on the position within the reactor, we're going to say it's a homogeneous material, so it's consistent all the way through, which will make our cross sections constants, which will simplify with solving this equation. We have no source. You can see in our equation we have no S or Q term, saying there's no source. We're saying no source, and then we're also saying one group or one speed, or also monoenergetic. This is also saying that our cross sections won't change with energy, saying that our neutrons are all one consistent energy throughout our reactor. So our equation here, with our assumptions here, our equation here is now going to become a lot simpler. So I should also put that this is 1D. So that just means our position vector is just x. So steady state, all time dependencies are 0, or all time derivatives are 0, and there's no dependency on t. So this whole term becomes 0. And just all our t's get crossed out. We have no time dependency. So we just have nabla dotted with d nabla phi of x. They have no dependencies for our cross sections, they're just constants. So here is what we're gonna mess with this next. Since we said we have a homogeneous material, our d is going to become a constant too, so that this nabla dotted with this quantity here is just going to become a nabla squared. We can pull d out too. So nabla squared of phi. Right now. So now, really, with nabla squared, since we're in one dimension, this is really just from the second derivative. So of d squared d phi dx squared. And I'm also going to pull our multiplying term, our fission, say our neutron production term, to the other side. Next, what we're going to want to do is we want to, get our second derivative here by itself. So we should divide by negative d. Get our second derivative plus. I'm also going to do this too. That negative sign is going to flip this around, so it's going to have nu of f sigma f minus a over d. And then we're going to factor out our phi, so we're just pull that out of it. Okay. So now we can simplify this even more That's by making this term equal to something, some constant. And we're going to choose b squared, and such that b is always greater than 0. So b is, well, even if it was negative, it would be still positive if we were squaring it. But we just want always a positive number, because this quantity here are nu f sigma f minus sigma a over d. That is always going to be a positive number. So we have that. We just rewrite this one more time. Plus b squared phi 0. Okay, so this is just a storm Louisville problem, SLP. It's common in a lot of physics applications, and usually you would set your eigenvalue equal to less than 0, 0, or greater than 0, but for nuclear engineering in this specific problem, it's always gonna be positive. So we're just doing the positive one, which is just b squared. Okay, so now this is just a second order ODE. So we can solve this using the characteristic equation. So we act like this is a constant, so we say r squared, and if there would be an imaginary first derivative there, but it's 0, so it's r, so it's 0 times r, and plus our coefficient in front of our phi here, so it's b squared equals 0. So it's r squared plus b squared equals 0. Solve for r, we're gonna get r squared equals negative b squared. Square root that whole thing. We're gonna get that r is equal to 0 plus minus b times I, our imaginary unit. So we have complex solutions. So we're gonna have an exponential of 0 plus minus bi, which we can just use Euler's identity to put it in terms of sine and cosine. So the general form would be e to the ax times sine, or c1, cosine bx plus c2 sine bx. Now our a is 0 and e to the 0 is just going to be 1. So this is going to change to c1. Should go down here. So our solution is equal to phi of x. Phi equals c1 cosine bx plus c2 sine of x, or bx. I'm going to have boundary conditions. So our boundary conditions for a slab reactor, 1D slab reactor. We're saying that we have a slab. Should have started with this, but we have a slab of x equals 0 to x equals a. And we're saying our neutrons are kind of going in from left to right, kind of. But our boundary conditions are going to be phi of 0 equals 0, phi of a equals 0. So we're going to say they're either going to get absorbed or like throughout, and they're going to be 0 at the end and 0 at the beginning. Those arrows. So now we're just plugging our boundary conditions to find our constants. So we have phi of 0 equals 0. When x is 0, so c1 cosine of 0 plus c2 sine of 0. Cosine of 0 is just going to be 1, and sine of 0 is going to be 0. 0 equals c1 cosine, or let's just be 1. So c1 equals 0. x equals C2 sine bx. Now we apply our second boundary condition. So when phi, or when x is a, 0, C2 sine of BA. Now, this is just a number. This is a number. So we could just divide by sine and then say C2 is 0. But if C2 is 0, then our solution is trivial, because then we're just saying that to solve this differential equation here, we can just say that phi is 0, then it solves everything. Or that's not this. We can just say phi is 0, and then it solves the equation, which is true, but it's trivial, because then we're saying we have no neutrons, we have no flux, no scalar flux in our reactor, when we know there is. So it's a trivial solution. Our solution is trivial. So this has to be true. So if C2 is not 0, that means sine of BA is 0. So now, if we kind of want to solve for B here, because it's the one thing we can control. So we take the arc sine of 0. So, and then, was arc sine of 0? Fuck. Yeah, okay. So then arc sine of 0 is just going to be n pi. Such that n belongs to all natural numbers. So it's 1, 2, 3, 4, 5, or I can be 0 too. So I guess you can include the 0. And that's because when if sine 0, pi, 2 pi, 3 pi, 4 pi, it's gonna all equal 0, and n just represents that it can be any one of those numbers. But for us to get a positive answer, and the definition of eigenvalues for nuclear engineering is that you take the greatest positive eigenvalue. So we're just going to do, and that's usually the first one. So we should do it's called a fundamental solution. Oh, that's not close, fundamental. And that's when n equals 1. So we have BA equals n pi, but we're saying the fundamental is when n equals 1, that we then have that B equals pi over A, where A is our length of our slab reactor. So if you pay attention to that, we have B equals pi over A, but we also have, we said earlier that B squared equals this quantity. So we have two things that B equals. So what does this mean? So this here, put over here, our B squared equals this. So this is it's called our material buckling. We consider B our buckling. So this is material buckling. This quantity here is just from our material. So this is a constant value. This is just from our material. So if we have a uranium reactor, depending on our enrichment or cross sections or what energy group we're looking at, this will change. And it doesn't really matter what our size is. This is all considered our geometric buckling. We're going to square this. Because this is our geometric constraint, you should say. And so for our reactor to be critical in a 1D geometry, or for any geometry, I should say, we need our geometric buckling to equal our material buckling. Kind of saying that our geometry and our material match in a sense. So in order to be critical, BG must equal BM. So it's just saying that pi squared over A squared equals nu F sigma F minus sigma A over D, our diffusion coefficient. So here now we can solve for our actual our length and find what length of our slab reactor needs to be in order to reach criticality for our multiplying system. So if we solve for A, we should do the quick trip of that. Flipping this, it's D over nu F minus sigma A, multiplying the square root. So then we'll say A equals, when we want the positive, even though taking the square root, we would have a plus minus on the outside, get the square root, but this value can only be positive. So let me look at the positive case. D pi squared nu F sigma F minus sigma A. So this is our, call it critical size, critical length of our reactor. This is what is needed to achieve criticality in our reactor. So we found our values for B here. What does this mean? So we have a value for B. We have that our phi of X looks like this. So bring this over here. So plug in B. We know that B is going to be pi over A. So our phi of X is going to equal C2, which we'll get to that in a second, over pi over A times X. And we're going to say that our C2 is it's easy to say that with knowing our physical intuition of what we're solving for, how our neutrons are going to be and stuff. Our C2 should be phi naught, kind of like our initial flux. So our final solution is going to be phi of X equals phi naught of sine pi over A times X. Now, what does this look like? What does this mean? So if we have our one-dimensional slab from X equals 0 to X equals A, it's just gonna kind of look like it's just sinusoidal, more of a sine curve. And in the center, so this would be X equals A over 2 over peak in the center, and on each end we're saying that 0. Now in reality there's a thing called extrapolation distance where this isn't 0 here, it's gonna cross somewhere over here and then cascade down. But for general purposes, we can just say it's 0 at the ends. So this is what our flux distribution is going to look like within our 1D slab. There's a nice sign, and yeah, that's our general solution to the neutron diffusion equation. And with our assumptions, 1D slab reactor, steady state, fixed law, homogeneous material, no source, and monoenergetic, one group.